So we have two beakers, A and B, containing strong bases. Beaker A has 500 centimeter cube of BaOH2 and then of unknown concentration, and then beaker B has 400 centimeter cube of potassium hydroxide KOH of concentration 0.1 mole per decimeter cube. And then 7.1 says define a base according to Arrhenius theory. A base according to Arrhenius theory ionizes to form hydroxide ions. So that's basically the definition of a base according to Arrhenius theory. A base ionizes to form hydroxide ions. And then 7.2 says calculate the number of moles of hydroxide ions in beaker B. So what makes up beaker B? In beaker B, we are told that in beaker B we have KOH, right? And then when this ionizes, it will give you K plus OH minus, right? We are given information about KOH. So from the information we have about KOH, we'll then be able to find the number of moles of OH. So let's go ahead and do that. So we are told that the concentration is equals to 0.1 moles per decimeter cube. And then the volume, it is given as 400 centimeter cube, which we have to convert to decimeter cube, right? We divide by 1,000, so we're gonna get 0.4 decimeter cube. Now we can find the moles of KOH and then use that to find the moles of OH using the balancing coefficients. So we're gonna get N of KOH is equals to C multiplied by V, right? We're saying that because we know that the concentration is equal to the number of moles divided by the volume. So we're using that formula. So N of KOH will be equals to, what is the concentration? 0.1 mole per decimeter cube. And what's the volume? 0.4 decimeter cube. This will give us 0.04 moles, right? And then now we can use this number of moles of KOH to determine the number of moles of OH minus, right? So we're gonna say the number of moles of KOH divided by the number of moles of OH minus is equals to 1 divided by 1, because that's the balancing coefficients. So basically the number of moles of OH minus is just equals to the number of moles of KOH, which is equals to 0.04 moles. And that's how you do 7.2. And then moving ahead, we have 7.3, which says the contents of beakers A and B are added together in beaker C. The solution is in beaker C has a pH of 13. So we have pH equals 13. And then from pH, before we go any further, we can determine the pOH, right? Because we know that pH plus pOH equals to 14. So that will say pOH equals to 14 minus 13. So pOH is equals to 1. Okay, let's move forward. So it goes on to say that assume that the volumes are additive and that the temperature of the solution is 25 degrees Celsius. And then 7.3.1 says calculate the concentration X of the BaOH2 in beaker A. So what is happening? Beaker A is being poured to beaker C, right? And then beaker B is being poured to beaker C. So beaker A has its own number of moles of OH, right? That will be poured to beaker C. And then beaker B also has its own number of moles that are going to be poured to beaker C. And then the number of moles in beaker A are unknown, but the number of moles on beaker N and in beaker B are known. And then we can use the pH to find the number of moles of OH minus in beaker C. So what we're gonna do, we're gonna find the number of moles of OH in beaker C, and then after that we'll subtract the number of moles in beaker B, and then what will be left is the number of moles in beaker A. So if we go ahead and do that, let's find the number of moles in beaker C. So we have POH equals to 1, like we determined above, right? And then we know that to calculate POH, we use the concentration of OH minus. So we're going to have minus log OH minus equals to 1. So we're going to have log OH minus equals to minus 1. And now to solve for OH, we can say OH minus is equals to 10 to the power minus 1. You can always do that, it always works. So if you take 10 to the power minus 1, you're gonna get OH minus is equals to 0.1. So we have the concentration of OH minus in beaker C. Now we can find the number of moles, right? So the number of moles of OH minus will be equals to the concentration multiplied by the volume, right? What's the concentration? It's what we just determined is 0.1. And then what's the volume? The volume, it is said to be additive, right? So we're going to add the volume of beaker A and the volume of beaker B. So that will be 500 centimeter cube plus 400 centimeter cube divided by 1000. And then if I get this, I put this in my calculator, I'm getting 0.09 moles, right? So now we have the number of moles of beaker C, which is equal to the number of moles of beaker B plus the number of moles of beaker A. The number of moles of beaker C is 0.09. The number of moles of beaker B is what we calculated in 7.2, and that was I think 0.04, right? And then plus the number of moles of beaker A. So the number of moles of beaker A will be equal to 0.09 minus 0.04, which is equal to 0.05. So now we have the number of moles in beaker A. So we can use that to calculate the number of moles of BaOH2. So BaOH2, when it ionizes, it becomes Ba plus 2OH, right? So we can see that the balancing coefficient is 1:2. So we're going to have the number of moles of BaOH2 divided by the number of moles of OH being equals to 1 divided by 2, right? So we're going to have the number of moles of BaOH2 equals to the number of moles of OH divided by 2. So that is equals to 0.05 divided by 2. If I put that in my calculator, I get 0.025. So now we have the number of moles of BaOH2. We can then calculate the concentration. We know that concentration equals to number of moles divided by V, right? The volume. The number of moles is 0.025, and the volume is the volume of beaker A, not beaker A and B added together. So we're going to have 500 divided by 1000. And then if you put this in your calculator, you're going to get 0.05 mole divided by decimeter cube, which is equals to X. And then we can move forward. 7.3.2, it starts with a statement there that says the solution in beaker C is titrate. The solution in beaker C is titrated with ethanoic acid. It was found the solution in beaker C is titrated with ethanoic acid. It was found that 15 centimeter cube of the solution neutralizes 30 centimeter cube of the acid, and then we are given a balanced equation. And then 7.3.2 says, is ethanoic acid a weak acid or a strong acid? At this point of time, you should know that ethanoic acid it's a weak acid. And then it says give a reason for the answer. In grade 12, you will only provide one reason for why an acid is weak. That is to say, it ionizes incompletely. And then 7.3.3 says calculate the concentration of the ethanoic acid, right? So they neutralized completely. So let me write the equation again. So we have CH3COOH plus OH minus, which is giving us CH3COO minus plus H2O. So again, we can use the number of moles of one to find the number of moles of the other. If you pay careful attention, when you are doing problems in chemical equilibrium and acid and base, you always relating the number of moles, right? You start with one and then you try to figure out the other and vice versa. So we have information for OH, which we can use to determine the concentration of the ethanoic acid. So we determine the concentration of OH minus in 7.3.1, right? And it was 0.1 moles per decimeter cube. And then we're given the volume to be 15 centimeter cube, which we'll have to convert to decimeter cube. So the number of moles from this will be given by the number of moles equals to the concentration multiplied by the volume, right? The concentration is 0.1 and then the volume is given as 15 centimeter cube. So that will be 0.1 multiplied by 15 divided by 1000. We divided it by 1000 because we convert it into decimeter cube. That will give us 0.0015 moles, right? We can see the balancing coefficient that this is 1 and this is 1, right? So the number of moles of OH equals to the number of moles of our ethanoic acid. So to calculate the concentration of ethanoic acid, we're going to say concentration equals to number of moles divided by volume. And then we know that the number of moles is the same as the number of moles of OH because the balancing coefficients are the same, right? So we're going to have 0.0015. And then what is the volume? The volume is given as 30 centimeter cube. So we're going to have 30 divided by 1000. Which is gonna give us, let me put that in my calculator real quick. So we have 0.0015 divided by 30 divided by 1000. That is equal to 0.05 moles per decimeter cube, and then you get your 18 marks. Two reactions of sulfuric acid are shown in the diagram below, and then the first question, which is 8.1.1, says define a Lorry-Bronsted base, right? This is the guy or the girl, not really sure, that defines a base and an acid the easy way, right? An acid, it's a proton donor, and then a base is a proton acceptor, right? So 8.1.1 proton acceptor, and you get 2 marks. And then 8.1.2 says write down a balance equation for reaction 1. Let's take our attention to reaction 1. So reaction 1, we have sulfuric acid H2SO4 and NaOH. So we have an acid plus a base, right? And an acid and plus a base. An acid and a base will always give you a salt plus H2O, right? That's just the general idea when you have an acid and a base. So we have H2SO4 plus NaOH, and this will give us something, right? Let me put the arrow here for the sake of space. So we need the acid to donate protons, right? And then we need the base to accept. So when the acid donates, we're gonna have this H2O here from the general formula, right? So we're going to have H2O. So if we have H2O on the acid, we're going to be left with SO4. So this Na, which was accompanying the OH, which turned to H2O, will be here with NaSO4, right? It will be our salt. But then I want you to realize something. Since H2SO4 lost 2 hydrogens, it will now be SO4 2 minus, right? And then we know that Na is only plus, so we're gonna need 2 NAs. So we're gonna have Na2SO4 plus H2O. Now when we're at this point, we can then balance our equation. So we have 2 hydrogens here, we have 1 here, and then here we have 2. So the hydrogens are not balanced. How can you possibly balance this hydrogen? If we put a coefficient of 2 here, we're going to have 4 on the right, and we're going to have 3 on the left. But if we put a coefficient of 2 here, then we have 4 on the left and 4 on the right. So now the hydrogens are balanced. We can look at S. We have 1 S here, we have 1 S here, so that is balanced. And then let's look at the oxygens. We have 6 oxygens on the left hand side, and then on the right hand side we also have 6 oxygen. So it seems like all is well, and we can move to 8.1.3. But for the most part, there's only a few reactions you're gonna be examined on, right? So just go to your exam guideline, go through past exam papers, and just memorize all the reactions that you see. And then 8.1.3 says, write down the name of the salt represented by X. So the salt represented by X is Na2SO4. What is Na? We know that Na is sodium, and SO4 is sulfate, right? And that is exactly what the name of our compound is. The name of our salt is sodium sulfate, right? But then it's not all the time that you just take the names of the different elements and then you just call it that. And then 8.1.4 says, let's write down the formula of ampholyte A. Ampholyte A is in our reaction 2, right? So in our reaction 2, we have H2SO4 plus H2O. And then it gives us, we know we're supposed to have H3O plus. So the sulfuric acid only donated 1 proton, right? So here we are left with HSO4 minus, right? So the name of our ampholyte is HSO4 minus. But is HSO4 minus an ampholyte? Yes, it is indeed an ampholyte. In this reaction, is acting as a conjugate base, right? But then if you say HSO4 minus plus H2O, then it's going to act as an acid. And then let's move to 8.1.5. Write down the formula of the 2 conjugate acid base pairs in reaction 2. So we've already written down reaction 2, right? Let's just look for the acid base conjugate pairs. So H2SO4 is an acid, and then when it loses the protons, we get the conjugate base, right? So if this pair is acid and base, then the other pair by default it will be our acid and base. So we can say H2SO4 and HSO4 minus is an acid base conjugate pair, and then H2O and H3O plus is another acid base conjugate pair. So whatever remains when an acid has donated a proton is the conjugate base, right? That's the rule of thumb. Now let's move to 8.2. 8.2 says a solution of sodium hydroxide NaOH is prepared by dissolving 6 grams solid NaOH in 500 centimeter cube of water. This solution reacts completely with 10 grams of impure ammonium chloride, NH4Cl, according to the equation below. And there we have our equation, and it says calculate the concentration of NaOH. So 8.2.1 NaOH. Problem solving 101. We have to write down the information we know about the NaOH, right? So we know fully well that the mass is 6 grams, and then the volume is 500 centimeter cube, and we want to find the concentration. Concentration is number of moles divided by the volume. So from the mass we can find the number of moles, and then we have the volume here. So let's go ahead and do that. So the number of moles will be equals to the mass divided by the molar mass. The mass is 6 grams, and the molar mass of NaOH is 40. So we're gonna have 0.15 moles, right? Now we can say that the concentration is equal to the number of moles divided by the volume, 0.15 divided by 500 centimeter cube, which you're gonna divide by 1000 to convert to decimeter cube. So we get in concentration of 0.3 moles per decimeter cube. And now we can move to the second question, which says let's calculate the percentage impurities in the NH4Cl. So let's break down percentage impurities. So we usually calculate percentage purity, right? So I'm assuming that percentage purity plus percentage impurity should be equal to 100%, right? So we can basically find the percentage purity, and then from the percentage purity we're gonna say 100 minus percentage purity is percentage impurity. Let me show you what I'm talking about. So we have 8.2.2. So we know that when we want to find percentage purity, we will need the mass, right? So let's say NH4Cl. So at the end of the day, we're going to need the mass, right? We know that initially the mass or mass total is 10 grams, right? We're going to find the mass. For purity, we will find the mass of the pure substance. So the mass that reacted, right? So let's go ahead and do that. What information do we have? Let's write our equation. NaOH plus NH4Cl is giving us NaCl and so on, right? So from the NaOH, we know that the concentration is equal to 0.3 moles per decimeter cube, and then the number of moles is 0.15 moles. And then we're supposed to use this information to ultimately find the mass of NH4Cl, right? Because there's no way we can find the percentage purity without knowing the mass. So how are we going to do that? We are definitely going to use the mole ratios of the two, right? Because in chemistry, for the most part, you're finding the number of moles and using it to find other quantities. So we can say that the number of moles of NaOH divided by the number of moles of NH4Cl will be equals to the balancing coefficient of NaOH is 1 and NH4Cl is 1. So now we're going to cross multiply. The number of moles of NH4Cl will be equals to 0.15 moles. The number of moles of NaOH multiplied by 1. So now we have the number of moles of NaOH. We can then find the mass of the NH4Cl that reacted, right? So the mass is given by the number of moles multiplied by the molar mass. We know fully well that the number of moles is 0.15, and then now we want the molar mass of NH4Cl. I think it is 53.5, right? So we get a mass of 8.025 grams, right? So 8.025 grams is pure, and then the remainder is impure, right? So we want to find the percentage impurity, not the percentage purity, right? So we know fully well that percentage purity is equals to mass of pure divided by mass of the entire sample, right? Multiply by 100. So percentage impurity will be equals to the mass of the impure, right? Divided by mass of sample multiplied by 100. It's a bit of, a trick equation, but not that much. So the mass of the impure, we're saying that initially we had 10 and 8.025 reacted, and then divided by the mass of the pure, which is 10 multiplied by 100, right? And that is 19.75%. You can do it even the other way that I suggested. You can find the percentage purity. So when you find the percentage purity, it will be 80.25%, right? So you would say 100 minus this value here, and you will still get 19.75%. So if you want the definition for 1 mole of a substance, then I've written it down in 6.1.1, right? You can just pause the video and copy it down. So what we're going to start with here is balancing the equation between sodium carbonate and hydrochloric acid, right? The equation is already given to us, but it's unbalanced, right? So that makes our job a little bit more easy. So let's go ahead and try and balance our equation. So on the left hand side, we have 2 atoms of Na, right? And then on the right hand side, we only have 1. So that means that the number of atoms of Na are not balanced. But how can we balance that? If we put a coefficient of 2 here, then we're going to have 2 atoms of Na on both sides, right? So now we can move from Na and go to carbon. On the left hand side, we have 1 carbon atom, and then on the right hand side we also have 1 carbon atom. So the carbon atoms are already balanced. We can move to the oxygen, right? Here we have 3 oxygen atoms, and then on the right hand side we have 1 here and 2 here. So we have 3 oxygen atoms on the left and the right hand side. So the oxygen atoms are balanced. Let's go to the hydrogens. Here we have 1 hydrogen on the left hand side, and then on the right hand side we have 2 hydrogens. We have H2, right? So the hydrogens are not balanced. How can we balance them? If we put a coefficient of 2 on the left hand side, then we're gonna have 2 hydrogens on the left hand side and 2 hydrogens on the right hand side. Now let's look at Cl, right? We have 2 atoms of Cl on the left hand side. On the right hand side, because of this coefficient 2 that we use to balance the Na, we also have 2 Cl, right? So now our equation is balanced. We only had to add 2 here on HCl and 2 on NaCl. Let's do 6.1.3. So 6.1.3 says calculate the mass of sodium carbonate that reacted, and then there's 7 marks. In order to do these questions, you have to be extremely sober. There's no other way around it, right? You have to be, extremely sober. So let's look at our statement, right? We are told that in an experiment, a learner added 1.5 grams of sodium carbonate, right, to hydrochloric acid. A volume of 306 centimeter cube of carbon dioxide was formed and collected under standard pressure at room temperature. Take the molar gas volume at room temperature as 24.45 decimeter cube, right? So let me just copy down the equation again real quick, because we have to use this equation, right? If we don't have the equation and we just writing things, then it becomes all over the show, right? There need to be clarity in our writing, right? So we are told that at the end of the day, we have a volume of 306 centimeter cube of CO2 produced. And for the sodium carbonate, we are given an initial mass, which is 1.5 grams, right? So of this 1.5 grams, not all of it reacted, right? That's why the question is asking us to calculate the mass that reacted. But how can we calculate the mass that reacted? Using the CO2, right? The volume of CO2 that was produced, we can find the number of moles of CO2 that we produce. And then with the number of moles of CO2 that we produce, we're gonna then use the mole ratio to find the number of moles of Na2CO3 that reacted. And from the number of moles, we can find the mass. Let me show you what I'm talking about. Let's not forget that here we have the balancing coefficients. So the number of moles of CO2, we're going to have the number of moles being equals to the volume divided by molar gas volume, right? If you have a volume of a gas, that's how you can find the number of moles. You use this formula here. So what is the volume? We know fully well that the volume is 306 centimeter cube, right? But then in chemistry, we don't use centimeter cube, we use decimeter cube. So what do? We divide by 1,000 from centimeter to decimeter cube. So we're gonna say divided by 1,000, and then we divide by molar gas volume. Is given to us as 22.45 decimeter cube. And then if you punch that in your calculator, you're gonna get 0.0125 moles per decimeter cube, right? So now we have the number of moles of CO2 that were formed with part of the sodium carbonate that reacted. Now using the mole ratio, we're going to be able to find the moles of Na2CO3 that reacted, and consequently the mass that reacted, right? So now we can say the number of moles of CO2 divided by the number of moles of Na2CO3 is equals to the balancing coefficient. What is the balancing coefficient on CO2? The balancing coefficient is 1, right? And then the balancing coefficient of Na2CO3 is also 1. Yeah, if you're still so confused and you don't even know what a balancing coefficient is this number here, right? You can see for NaCl the number is 2, for HCl the number is 2, for Na2CO3 we don't have anything, right? But we actually have, it's 1, right? And then for CO2 it's also 1. Just in case. So now we can say that the number of moles of Na2CO3 will be equals to, we cross multiplying with multiplying everything by 1, right? So it will just remain how it is. It's equals to the number of moles of CO2 being equals to 0.0125 moles per decimeter cube. So now we have the number of moles of Na2CO3 that reacted, and we can then find the mass, right? Because we know fully well that the number of moles is equal to the mass divided by the molar mass if you're dealing with a solid, right? So now we can say that this is for Na2CO3. Let's not forget that. So now we can say that the mass is equals to the number of moles divided by the molar mass. We cross multiply, right? So we're going to have 0.0125 multiplied by the molar mass of Na2CO3. It's 106. You can verify that on your periodic table, right? And then the answer we get in now is 1.33 grams, right? So that's the mass of Na2CO3 that reacted, right? Let's do 6.1.4. Calculate the percentage of sodium carbonate in excess. So we have the mass that reacted, right? We have the mass initial that we started with, right? So we can find the mass in excess, right? Because let's say for Adam and Eve's sake, right? You have initially you had 5 apples, and then something happens to your apple, and then after, right, in excess, basically you have 2 apples. How many apples were used? You would say 3, right? So this is just telling us that the mass that is used is equals to the mass initial minus the mass in excess, right? You cannot deny for Adam and Eve's sake. So the mass initial is given to us as 1.5, right? The mass in excess, that's what we're looking for, mass in excess, right? And then the mass used is what we calculated here, right? We have 1.33. So now you're going to take this term to the left hand side, right? You're going to have 1.33 minus 1.5, right? And you're going to get minus 0.17 being equals to minus the mass in excess, right? It's easy, divide both sides by -1, and then the mass in excess is equals to 0.17 grams, right? So now we can say that the percentage of CaCO3 in excess, right, will be equals to, so we have 0.17 divided by the initial mass, which is 1.5, multiplied by 100. Obviously, we want the percentage. So that will be 11.33 recurring, right? And so on percent. You can see here the kind of stuff we do in that you have no choice. You have to be, extremely sober, right? Let's do 6.2. 6.2 is saying that zinc reacts with sulfuric acid according to the reaction below, right? And then there we have our reaction. The mass of zinc is recorded during the experiment and is shown on the graph below. The reaction stops after 2 minutes, right? So let's analyze our graph for just a second. Initially we had a mass of 5 grams, right, at t is equals to 0, and then after some time the mass is now 2 grams and it stays at 2 grams, right? And then 6.2.1 says name the substance that is the limiting reactant, right? Let's analyze our situation. We have zinc and sulfuric acid, right? The mass of zinc starts at 5 grams, right, here, and then at 2 grams it never goes down, it remains there. Clearly, what was causing the mass of zinc to be converted to something else is depleted, right? So zinc is being limited by something it's reacting with here, and the only thing it's reacting with is sulfuric acid, right? So the substance that is acting as the limiting reagent is the sulfuric acid, right? So 6.2.1, you just say sulfuric acid. And now we can do 6.2.2. 6.2.2 says calculate the initial concentration of the sulfuric acid if 50 centimeter cube of the acid was used. All the time when I have a question like this, I'm going to write the formula down, right? If I cannot see the formula on the answer sheet, it's just too confusing for me. So I have the zinc plus H2SO4 giving me ZnSO4. I don't know what the name of that is, plus H2. Stories. The question is saying from the sulfuric acid, let's find the initial concentration, right? But because you are a chemist, we know that to find the concentration, we need the number of moles and the volume, right? But I kid you not, they've given us the volume here. So what we want is only the number of moles. We know that the volume is equals to 50 centimeter cube, right? Which we are obviously going to convert to decimeter cube. So we want the initial concentration. So we need the number of moles of H2SO4, right? the number of moles of H2SO4. How can we find that? We can use zinc, right? Because we know fully well the mass of zinc that reacted, right? Again, for Adam and Eve's sake, initially we had 5 grams of zinc, and then after some time we have 2 grams. So how much reacted? It should be clear to see that 3 grams of zinc reacted, right? So now we can say that with regards to zinc, we know that the mass that reacted is 3 grams, right? So from the mass, we can find the number of moles of zinc that reacted. And from the number of moles of zinc that reacted, we can use the mole ratio to find the number of moles of H2SO4. If we have the number of moles and we have the volume, we have the concentration, and we are done with our problem, right? So let me show you what I'm talking about. Now we say that the number of moles is equal to the mass divided by the molar. So what is the mass? The mass is 3, right? And the molar mass of zinc, that is 65. And when you punch that in your calculator, you should get 0.0462 moles, right? Again, the mole ratio. So the number of moles of Zn divided by the number of moles of H2SO4 should be equals to the ratio of the balancing coefficients. So we have 1 divided by 1, right? So the number of moles of H2SO4 is equals to the number of moles of zinc, which is equals to 0.0462. I wish we had a problem where the balancing coefficients were not 1 and 1, because I feel like people will make mistakes, because in other questions you might not get 1:1. So make sure you go and watch other videos on acid and bases so that you can see how you manipulate this kind of equation when you don't have a balancing coefficient of 1 and 1, right? But yeah, stories. So now the number of moles of H2SO4 is that, right? And then now we can find the concentration. That's what the question is asking us to do. Concentration is equal to number of moles divided by volume. So we have 0.0462 divided by the volume, right? 50 centimeter cube. Obviously, we're going to divide it by 1,000. We deal with decimeter cube. We are chemists, right? And when you punch that in your calculator, I wish you get 0.92 moles per decimeter cube. 7.1.1. Is ethanoic acid a weak acid or a strong acid? Give a reason for the answer, right? So I'm gonna say it's a weak acid, right? Why am I saying it's a weak acid? I'm saying it's a weak acid because it's an ingredient of household vinegar, which you've probably used at some point of time. And if you pour a bit on yourself, you don't get burnt in any way. So it's a weak acid, right? But then when they say give a reason, they don't want you to say that. They now want the technical reason why it's considered a weak acid. So what is the technical reason? It's considered a weak acid because it dissociates partially in water, right? That's the reason they're looking for. So you're gonna say dissociates partially in water. And then we have 7.1.2. It says an ethanoic acid solution has a pH of 3.85 at 25 degrees Celsius. Calculate the concentration of the hydronium ions H3O plus in the solution. So fine, we know that pH is equals to minus log and then H3O plus, and then the pH is given to us as 3.85. So 3.85 will be equals to minus log concentration of H3O plus, and then we multiply everything by minus 1, right? So we're gonna get minus 3.85 equals to log HO3 plus, And then we can say that the concentration of H3O plus is equals to 10 to the power minus 3,85. And then if I put that in my calculator, I'm getting 1.41 times 10 to the minus 4 moles per decimeter cube. And then we have 7.1.3, which says sodium ethanoic CH3COONA, right, forms when ethanoic acid reacts with sodium hydroxide. And then it says, will the pH of sodium ethanoic solution be greater than 7, less than 7, or equal to 7? It's definitely gonna be greater than 7. Why is it greater than 7? We know now that ethanoic is a weak acid, right? So we have a weak acid being combined with a strong base, because sodium hydroxide is a strong base, right? So if you combine these two, you're gonna get a base, right? You will have a pH of greater than 7. So if instead you had a strong acid and a weak base, then the pH would be less than 7. And then we have 7.1.4, which says explain the answer to question 7.13 with the aid of a balanced chemical equation. So let's put sodium ethanoic in water and see what happens. So we have CH3 COONA plus H2O, and then this is supposed to give us something, right? So because we're saying that this is a base, right, because it has a pH of greater than 7, so this has to be an acid. So a base will accept a proton, right? And then the acid will donate a proton consequently. So if CH3COONA accepts a proton, we're gonna have CH3COOH plus NaOH. So we can see that we have hydroxide here, and as a consequence, the pH will be basic. So let's move forward and go to 7.2. 7.2 says household vinegar contains 4.52% of ethanoic acid, CH3COOH by volume, right? And then 1.2 gram of impure sample of calcium carbonate is added to 25 centimeter cube of household vinegar. On completion of the reaction, the excess ethanoic acid in the household vinegar is neutralized by 14.5 centimeter cube of a sodium hydroxide solution of concentration 1 mole decimeter cube. And then we have a balanced equation for the reaction. That's a mouthful, but let's see what we can do. So we have 7.2.1 saying calculate the number of moles of the unreacted ethanoic acid. So it is said that the excess ethanoic acid is neutralized by sodium hydroxide, right? So we're gonna have NaOH. This NaOH neutralize the ethanoic acid. But then we are told that the volume that does the neutralization is 14.5 centimeter cube, and then the concentration was 1 mole decimeter cube per decimeter cube, right? So what we can do, we can find the number of moles of NaOH related to the number of moles of ethanoic acid, and we're basically done, right? So from here we can see that the number of moles is equal to the concentration multiplied by the volume. We know the concentration fully well, that is 1, and the volume is 14.5 divided by 1,000. By now you should know why I'm dividing by 1,000. I'm converting the centimeter cube to decimeter cube. So if I divide that by 1,000, it's giving me 0.0145 moles, right? So now I want you to look at something. The balancing coefficient of our ethanoic acid is 1, and the balancing coefficient of our NOH is 1. So the number of moles of NaOH is equal to the number of moles of CH3COOH, and then that will be 0.0145 moles. But what if the balancing coefficients were not the same? I've solved a similar problem with that kind of situation, so I would advise you to go and check it out. So moving forward, we have 7.2.2, which says calcium carbonate reacts with the ethanoic acid according to the following balance equation, right? And then it says calculate the percentage of calcium carbonate in the impure sample if 1 centimeter cube of household vinegar has a mass of 1 gram. So what this question basically wants us to do is calculate the percentage purity of calcium carbonate, right? And then when we calculate in percentage purity, we'll always end up saying the percentage of the whatsoever we have, right, is equal to the pure divided by the impure and multiplied by 100. We have the pure, it's 1.2 gram is given to us, and now what we need to determine is the pure, right? But then how would we go ahead and do that? We need to find the number of moles of ethanoic acid that reacted, and by using that we can then relate the number of moles using the balancing coefficients and consequently found the mass of the calcium carbonate. So for the number of moles of ethanoic acid that reacted, we still need the mass initial, and to determine that we're gonna say that the mass is equals to 4.52 divided by 100 multiplied by 25. Why am I saying that this will give us the mass? Because usually the mass is the number of moles by the molar mass. So look at this. This is the percentage of ethanoic acid in household vinegar, right? And then we are told in the equation that 1 centimeter cube, we can take it as 1 gram, right? So that's exactly what I'm doing there. So we're gonna have 4.52 divided by 100 multiplied by 25, which is equals to 1.13 grams, right? And from this 1.13 grams, we can then calculate the number of moles of ethanoic acid initial, right? So we're gonna say the number of moles is equal to the mass, obviously, divided by the molar mass, which will be 1.13 divided by the molar mass of carbon is 12 plus 3 for the 3 hydrogens plus 32 for the oxygens plus 1, right? So let me punch this in my calculator real quick and see what I get. So divided by 12 plus 3 plus 32 plus 1 plus 12 again. I just missed the carbon there, and this is giving me 0.0188 moles, right? So now because we have number of moles in initial, right, and we have number of moles that are in excess, right, that didn't react, we can then calculate the number of moles that reacted. So we're gonna say number of moles that reacted equals to number of moles initial minus number of moles in excess, right? So the number of moles that reacted will be equal to the number of moles initial, which is 0.0188 minus number of moles in excess, which we calculated in 7.2.1, right? That is 0.0145, and then let me put that in my calculator real quick. That is 0.043. So now we can determine the mass of the calcium carbonate, right? So we can say that the number of moles of our acid divided by the number of moles of our base basically is equals to what the balancing coefficient of the acid is 2, right? And for the base is 1. So we're gonna say that the number of moles of the base equals to 0.043 divided by 2. If I do that, let me see what I get. It's giving me 0.00215. So from that 0.00215, we can calculate the mass of calcium carbonate, right? So we're gonna say that the mass is given by the number of moles multiplied by the molar mass. So this will be 0.00215. And what's the molar mass of calcium carbonate? That's 100, right? Which is 0.215, right? So now we can come back to our formula for the percentage purity, right? And then for the impure, we can then put 1.2, and then for the pure, we can put 0.215. And then if we multiply that, we're gonna get about 18.08, right? Or something somewhere there. The following apparatus is used for the titration of a dilute alkali with a dilute acid, and we're given a balanced equation. And 7.1.1 says, what type of a reaction takes place when an acid is added to an alkali? An alkali is basically a base, right? So we have an acid and base reaction. So 7.1.1 acid and base reaction. Another name for an acid and a base reaction is neutralization, right? So you can write acid and base, or you can write neutralization. Now let's move to 7.1.2, which says that write down the name of the dilute alkali. So the acid is H2SO4, right? Which is basically sulfuric acid. Ba is barium, right? And then OH, you usually pronounce it as hydroxide, right? If you remember, if we have NaOH, this would be sodium hydroxide, right? So this will consequently be barium hydroxide. So here 7.1.2, we have barium hydroxide. 7.1.3 says, name the pieces of apparatus labeled X. So here's X here. You should be familiar with X at this point of time, right? X is a burette. It's essentially a glass tube, right? With readings on it, and it has a turning plug here, right? To control the amount you're putting in on your beaker or whatsoever you're using. So 7.1.3, we have a burette. And then 7.1.4 says methyl orange is used as an indicator. What will you observe in Y when the acid is added before the endpoint is reached? So before we add any acid, right, you are going to basically have a base, right? If you add methyl orange to a base, then the methyl orange is gonna turn yellow. So what we are going to observe between before the endpoint is reached is that the methyl orange turns yellow, and then as we add more acid, it will gradually turn to orange as we reach a pH of around 7. And then if you keep on adding more acid, and now the solution actually becomes acidic, then the methyl orange will turn red. So for 7.1.4, the methyl orange turns yellow because we add it into a base, and gradually turns orange. And if you keep adding more acid and your solution becomes acidic, it will consequently turn red. And then 7.1.5 says, state whether each of the following increases, decreases, or remains constant while the acid is being added before the endpoint is reached. So back to the basics. What's an acid? An acid is a proton donor. So when we increase the acid, we increase in H+, right? So what will happen to BA to the 2+, right? We won't have any effect on BA to the 2+ when we increase the acid, right? So BA2+ will remain constant, right? And then what will happen to OH-? The concentration of OH- will go down when we add H+. Why am I saying that? So before we started adding the acid, right, we just had BaOH2 giving us Ba to the 2+ plus 2OH-, right? So when we add the acid H2SO4, the Ba2+ will react with SO4 2-, and then the OH- will react with 2H+. So the more we add the acid, the more the concentration of OH- decrease, right? Because OH plus H is clearly H2O. So here for OH- is going to decrease. So for pH, we know that the pH is equals to minus log of H+. The more you increase the concentration of H+, the lower the pH will be, right? So as we increase H+, the pH will consequently decrease. And then now we can do 7.1.6. 7.1.6 says that during the reaction, 50 centimeter cube of the dilute alkali reacts completely with 30 centimeter cube of the dilute acid. So the dilute alkali is reacting completely. That tells us that the dilute alkali is our limiting reactant, right? And then the question goes on to say, calculate the mass of barium sulfate that will form during the reaction if the concentration of the dilute alkali is 0.1 mole per decimeter cube. So we have the dilute alkali BaOH2, right? And then we are given the concentration. It is said to be 0.1 mole per decimeter cube, and then we are given the volume, which is said to be 50 centimeter cube. So if we find the number of moles of BaOH, then we're gonna be able to use those number of moles to find the number of moles of barium sulfate, right? And from the number of moles of barium sulfate, we'll consequently be able to find its mass, because that's what the question is asking us to do, right? So here we're gonna have the concentration is equal to the number of moles divided by the volume. If you make the number of moles a subject of the formula, you get concentration multiplied by volume. So what's the concentration? The concentration is 0.1, and what is the volume? The volume is 50 centimeter cube, right? But we deal with decimeter cube. So here we're going to have 50 divided by 1,000. So 50 divided by 1,000. So we basically have 5 divided by 1,000, which will be close to 0.005 moles, right? So if we go back to our equation again, the balancing coefficients, we have 1, 1, 1, right? So the number of moles are basically equal for all those three that I just indicated there. So the number of moles of BaOH2 will be equal to the number of moles of BaSO4. So that will be 0.005 mole, right? Now we can calculate the mass of barium sulfate. We have the number of moles, and the molar mass, we can get it from our periodic table. So now we know fully well that the number of moles is equal to the mass divided by the molar mass. If you make the mass of the subject to the formula, you get number of mole multiplied by the molar mass. So what is the number of mole? What we just calculated, right? So we have 0.005 multiplied by the molar mass of barium sulfate. If you add the molar mass of barium and SO4, that will give you 233. So 233 multiplied by 0.005, that is 1.165 grams. So the mass of the barium sulfate that will be formed will be 1.165 grams. I hope that is clear. Let's just recap for the last time. We're given the concentration and the volume of dilute alkali or barium hydroxide, right, which was used, and then we figured out that it's our limiting reactant, right, because we are told that it reacts completely. So from there we find the number of moles of the alkali, the dilute alkali, and we use those number of moles to find the number of moles of the barium sulfate, right? And from the number of moles we calculate in the mass here, right? High school chemistry is basically finding the number of moles of one reactant and using it to find the number of moles of the other, and from there you'll find either the concentration or you'll find the mass. And then 7.2 says 2 test tubes contain solutions of NH4 plus, I think, and CH3COONA. Their pH values are less than 7 and greater than 7 respectively. Write down the following rewrite the following hydrolysis equation in the answer book and complete them to explain this behavior. So for NH4 plus, we are told that the pH is less than 7, right? So if it is less than 7, it is acidic, and if it's acidic, then it's a proton donor, right? So that NH4 plus is supposed to lose a proton, it's supposed to lose one hydrogen, right? So here we're gonna have NH3, right, instead of NH4, because now we have lost a hydrogen, plus H3O plus, right? And then that's basically what you're being asked to do. And then now let's pay our attention to 7.2.2. It is said to have a pH of greater than 7. What does that tell us? It tells us that it is basic, so it's supposed to gain a proton, right? So we're gonna have CH3COOH, right? There we go, we have gained a proton, plus now the proton is coming from H2O, right? So the H2O now will be OH minus, and then now so the hydrogen that NH4 plus lost came to H2O, right? So hence here we have H3O plus.